Chapter 2, these are the think and rank problems. So let's just sort of work through those. So problem number 31, the weights of Burl, Paul, and the scaffold produce tensions in the supporting ropes. Rank the tensions in the left rope from the most to least in the three situations A, B, and C. So this comes down to, we can go through an analysis, and to do proper math analysis, we really need to bring in some Chapter 8 stuff. So we're going to skip over the proper math and do more towards the concept. Hey, it's conceptual physics. What the heck? So if we assume that Burl and Paul weigh the same amount, then it would make sense that the left and right, so in part A, the left and right ropes would have the exact same tension in them. The tension is the force acting up on the scaffold. And the rope that's going to take the most of it will take the extreme. Let's say if Burl and Paul are both right there at the left rope, then that's just like they're hanging on the left rope, and the right rope's only just dealing with the scaffold. So the closer they are to the left side, then the more tension that's going to take. And so looking at it, C would have to have the most tension in the left rope, B would be the next, and then A would have the least amount because of, well, if we go with Burl's on the left side, Burl doesn't move, but Paul is in different spots. Paul's getting closer and closer to the left side. Problem 32, let's see if I can adjust this. I'm not sure that's any better. So 32, we're looking at the net force. And I do have to throw in one other thing. Hewitt has many times where he makes some, he leaves certain words out that really should be there. Properly, this should be rank the magnitude of the net force, not just the net force, because then you start getting into plus and minus. So what he's really asking is the magnitude of the net force. Now, magnitude is, I'm ignoring the direction of the total force. I'm not ignoring the direction of each individual force, just the total at the end. So in part A, I have 10 newtons to the left and 5 newtons to the right. Well, the total force is 5 newtons to the left. That, when you add them together, you have to take direction into account. I've got something 10 this big and something 5 that big. The remainder right here is the part that is the net force, because they're in opposite directions. So that is 10 newtons, or sorry, the total is 5 newtons to the left. In B, I have 7 to the left, 3 to the right, so that's a net of 4 to the left. C, I have a net of 8 to the left. D, I have 3 newtons going in both directions. The total force is 0. It's being like in a tug of war, people pulling on me, and, like I have 2 ropes right there trying to prevent 2 people from ripping me in 2. And if they're pulling with the equal force on both sides, then I'm not going at least my center of mass isn't moving. What the heck, let's just assume my arms are strong enough that I can hold them in place. But my body is not moving one way or the other. So, recapping for A, B, C, and D, the magnitude of the net force was 5 newtons, 4 newtons, 8 newtons, 0 newtons. So C is the greatest magnitude, then A, then B, then D. Number 33, rank the different materials A, B, C, and D, rest on the table. Rank how much they resist being set into motion. So resistance to change is dealing with inertia. And inertia is a concept, it is not a quantity, but we do have a measurable quantity which tells us how much inertia an object has, and that is mass. So mass is related to the inertia. And so if we look at it, when we're ranking from how much they resist being set into motion, we're just ranking masses from greatest to least. And they tell us the masses right there on the problem. So the iron, 15 kilograms, is the greatest resistance. So that's B, then A, then C, then D. Rank the support force the table exerts on them from greatest to least. This deals with the support force is offsetting the weight. If they are in equilibrium, it says they're at rest, but more importantly, they're not accelerating, which is not the same thing as at rest. If they are not accelerating, then the forces up equal the forces down. If it's not accelerating, it is in equilibrium. If it's in equilibrium, the total force is 0. So forces up equal to forces down, which means that the support force up, what we in class will call normal force, the normal force up must be equaling the weight down on the object. Equal in magnitude, opposite in direction. That is not Newton's third law. Even though the same words are used there, it is not Newton's third law. The forces up equal the forces down. And so it comes down to the weight. Now, the weight and the mass are not the same. Please, if nothing else you take from this, mass and weight are not the same thing. Now, I understand everyday language, people often use them interchangeably, and some of the other sciences, they will use them interchangeably, but in physics, we make that distinction. There's a very clear difference between the two. However, there is a direct correlation between weight and mass, assuming that you are roughly in the same place. Now, these are roughly in the same place if they're all sitting on this countertop. So the acceleration due to gravity will be roughly the same for all of them. Now, acceleration due to gravity is something we'll get into in Chapter 3. I'm pointing like Chapter 3's over there. Well, in Chapter 3, so the iron, the 15 kilogram iron will have the greatest weight, then the sand, then the water, then the pillow. So it's the same order as in Part A, but it is possible for them to have a different order if they are in different locations. So, number 34. Now, number 34 also shows up in I think it's Chapter 5, page 87, number 33. It's the same problem, but we have 3 pucks that are sliding along ice at noted speeds. At the noted speeds. And they give them on the other page, at the top of the next column. Air and ice friction forces are negligible. So the only forces we have acting on this, if we do the force diagram, we have normal force acting up and we have weight acting down. There's no force keeping them moving. Newton's first law. An object in motion will stay in motion at a constant velocity unless acted on by a net outside force. So rank the forces needed to keep them moving. It doesn't require anything to keep them moving. The only forces we have are up and down. They are balancing each other out. They are neutralizing each other. The puck is not grinding into the ice or lifting off the ice. It is just moving horizontally, perpendicular to those 2 forces. There's nothing that says that they are going to stop. Objects will travel at a constant velocity unless a force causes it to change. So, therefore, it requires no force to keep them moving. Part B, rank the forces needed to stop them in the same amount of time. That will be different. The faster it's going, assuming all the pucks are the same mass, if the masses were different, we'd have to get into more sophisticated arguments, and that would show up in Chapter 6. Chapter 6 is when we deal with that. But they're all the same mass. The faster it's going, if we want to stop them all in the same amount of time, greater force will correspond to the greater speed. And so that would be ranked CBA, since C is traveling the fastest. 35, as seen from above, a stubborn stump is pulled by a pair of ropes with a force, each with a force of 200 newtons, but at different angles as shown. From greatest to least, rank the net force on the stumps. All right, so we do have a force on this, and the question is, are the forces helping each other, hurting each other, or, independent of each other? So looking at it in Part B, the 2 forces are actually sort of helping each other. There's the angle between them, math-wise, the angle between them is under 90 degrees, so they are helping each other. In C, the forces are, it's an obtuse angle. Part of this force is countering this force. And so that is going to weaken the overall force. It's be like trying to pull the tree, take the extreme. If you're trying to pull it out and you're pulling in opposite directions. If you're pulling in opposite directions, that stump's not going to move. Presumably, it'd be very difficult unless one of you pulls with so much more strength to overcome the other one. So, and then A, they're perpendicular to each other. That's the, math-wise, that's the simplest case. We can find the total force using the Pythagorean theorem. Officially, that's Chapter 4. They moved it around in the book where that shows up. So we'll talk about that in class. But in terms of ranking, B would be the greatest, then C, then A. Scratch that. B would be the greatest net force, magnitude of a net force. A would be next, and then C is the least, because in C the 2 forces are acting sort of opposing each other. And then in 36, Nellie hangs motionless from the clothesline. Which side, A or B, has the greater tension? This is similar in math-wise to problem 31, which of the 2 ropes holding the scaffold and the 2 people, which one has the greatest force on the left side? This is left over here. And in A, line A is closer to the horizontal. It is going to take the brunt of Nellie's weight. Now there's a vector way of doing it. If you ask in class, I'll do the vector way also. But if you take the extreme, if A is coming straight down and B is off at an angle that way, A will be taking all of Nellie's weight. But it's not quite horizontal. It is at a slight angle, but A is going to take the brunt of it. So that is the think and rank.